Good guys, so most of you know me, I'm Nicholas Crouch from the Maths Learning Centre, and we're here to do a bit of revision for AQMF. So really, this is a bit freeform, as in I don't have a plan. That means if you've got something you want me to talk about, feel free to tell me about it and I will go through it. If not, I printed out a couple of recent exam papers and I can sort of talk about stuff in them for one of the better things to do. Alright, so do we have anything we want to go through? Gentlemen in front, you look like you might have questions.
There we go, summation.
Beg your pardon? Summation stuff. Ooh, okay. So what we might do, we've got your oldie textbook, so we might actually have a thumb through to the appropriate page in the textbook. Did I remember to say record is the question we're going to ask ourselves? Yes, we are recording. Awesome. One of the other things you've got to do at the end of this session is remind me to upload the file so that we actually have a video. Summation. Is this thing going to talk about summation? Summation notation. Alright, 926. Okay. Oh, okay. I think what we'll do, so we'll do a little bit that runs along the lines of an introduction, and then we will elaborate a little bit on how we might use that. Okay, so chiefly where you're going to be asked about summation stuff is doing upper and lower sums. Okay. So all of this stuff that I'm writing on the page here will get scanned and uploaded with the seminar, so you'll be able to get stuff I've scribbled, the stuff that I've got here. You get the recording, which is I'm sure exciting, and then from there, what you do with it is your own business. So first thing, so if we're going to do something on summation, might as well do this properly. First thing we've got to know about our notation. The symbol we know is a capital sigma from the Greek alphabet. I'm going to say I is equal to 1 to n of, I'm just going to go with I. So one of the first pieces of advice I have when you get this sort of thing is know what the notation means. So literally we read this as the sum of I from I is equal to 1 to n. Alright, so if we get a particular example, so we go sum I is equal to 1 to 10 of I, that literally means 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. Okay? Awesome, right? And we've all had a bit of a look at this and gone, the answer is 55, yep. Can't write a page, you can't write a sum on a page without telling you what it is. So, the idea of using this notation is it simplifies what we're expressing. Okay, we want to get a simpler notation for the total for the sum. Newton actually invented a thing called, what was it? They actually invented an index notation, I think it's called. Newton, Einstein, I forget. Anyway, the point was, we want to, if we've got a really complicated thing, if we can express that complicated thing in a simpler way, it's easier for us to work with it. So my first advice whenever we're faced with a sum, actually write out the first few terms, write out the last couple of terms, see what you've got. So if you had a sum which said like 4i minus 7, alright, if I'm doing this from I is equal to 5 to 11, don't know what it is, alright, I've made it up somewhat arbitrarily, but if I write out what these numbers are, so if I put in I is equal to 5 in here, so I'm going to get 4 times 5 minus 7, so 4 times 5 is 20, minus 7, it's going to get me 13. plus I. So I started with I is equal to 5. So I move on to I is equal to 6. So that's what it means. The sum said for each value of I between 5 and 11, work out what this number is, add it to the total sum. So 6, so 24 minus 7 is going to get me 17 plus, I can basically add 4 to this, each one of these numbers and get myself 21 plus 25 plus. So how many should I have? So I is equal to 7, I is equal to 8, 29, that's I is equal to 9, I is equal to 10, should be 33 plus 37, that's I is equal to 11. So, and we stop when we get to this number, when I reaches 11. So we include I is equal to 11, but we stop there. So this particular one, I'm actually not going to work this out just by adding those numbers up. There's only, what, 7 of the numbers? But 7 is like too many for me to work out in my head, so I'm not going to do it. All right. The other one, I happen to know the answer, so I'm just going to do it. But what I can do, right, with these numbers, if you imagine this number is like 20 minus 7, and then 24 minus 7, and then 28 minus 7, 32 minus 7. I'm going to go right up to 44 minus 7. That's my last number. Add in some dots to say I didn't write them all down. Then what I can do is I can group them into bits. So I can do the 20 plus 24 plus 28 plus 44 minus, and then I've got 7 plus 7 plus 7. Now, just by knowing that there are 7 of these numbers, I know this is going to be 7 times 7. So I'm going to take off 7 times 7. Whoops. Yes, watch for that. Alright, we should understand that it's actually been a few years since I've actually lectured on a regular basis, and so I forget little details like make sure the students can actually see what you're writing. So don't be shy about telling me that I stuffed up, because I will. In short, I'd like to say otherwise, but I just stuff up. I write the wrong numbers down. Now these other numbers, I can take a factor of 4 out of them. They're all divisible by 4, so I can write this as 5 plus 6 plus 7 plus 11. All right, getting there. Yes. Now, my next trick, 4. So I've got my, what I'm going to do is I'm going to go 1 plus 2 plus 3 plus 4, and then I'm going to go plus 5 plus 6 plus 11. And then I'm going to take off these numbers, 1 plus 2 plus 3 plus 4, minus 49. Now what I've done is I've made this a nice continuous run from 1 to 11. Okay? Now, so I added in the numbers that I needed, the missing numbers that were at the front, from 1 to, so that my sum is now from 1 to 11. And because I added them in, I'm going to take them off so that the net result on my sum is 0. Now these numbers here, I can tell that's nice and easy to add up, that's 10. And because I've added these ones up, all except for the 11, if I just add 11 to that, I can go, this is 66 minus 10 minus 49, which is going to get me 4 times 56 minus 49. So that should be like 224, let's pretend. 224 minus 49, so take 50 from that, so 175. Take 50, add 1, got me a number. I have no idea if this number is correct or not, but I'm going to believe it, all right? One of the other things we should do when I do these things, when I do mental arithmetic on the fly, whoops, you can't see that. When I do mental arithmetic on the fly, I may make a mistake, all right? But the idea, the concept behind what I'm trying to do is sound. So, got myself some idea of what this thing is. So, but let's try and formalize what we did here. If we go back a little bit, you see how I've sort of broken my sum up into the bit that changed and the bit that remained the same? So I split up the 4i bit and the +7 bit. So exactly, I could have written that without having to write out all those numbers, because let's face it, we're not going to write out all those numbers in the exam, are we? If in doubt and you have lots of time, write out all the numbers, add them up. But you don't have that much time in the exam. So if I take my sum, I is equal to 5 to 11 of 4i minus 7, what I can do is I can split that. That's the 4i bit and the -7 bit. So I can write this as sum I is equal to 5 to 11 of 4i plus sum of -7 I is equal to 5 to 11. Okay. Perhaps the best thing to do is pick on one bit at a time. Alright, that's the other thing you'll see us do. Alright, we've got all these wonderful formula. Let's just take one bit, break it down, work out what it's telling me. So, and that's, when we do it, it means what we're saying is it's a good idea and you should be doing it as well. Okay, too many students go, yeah, the lecturer did that, but I didn't think I'd do that. Possibly a lack of confidence. If the lecturer says just do this, one of the tricks to do is to try it. Alright, my favourite story is, I used to love the idea of making pasta. And so Jamie Oliver is sitting on the television telling me that if I just do this, whack it in a processor, do this, knead it for a bit, whatever, run it through a pasta machine for a bit, I'll have beautiful pasta. And I'm like, alright, I'm going to do exactly what he said. I'm going to follow it as near as I can remember it. Anyway, ended up with some beautiful pasta. More or less, not sure whether it was accident or what, but just by following the instructions given by an expert, I ended up with what I was looking for. Now, with this thing here, every number is -7. So I could have taken a factor of 7 out of all of these, put my -7 out the front. Okay? And what I would have been left with is sum of 1. Alright? From I is equal to 5 to 11. So what I could do then is I could shift my index. Alright? I can shift this index. So if I take 4 from here and 4 from here, I would add, ideally, I would add 1 to the I that was in this term, but there is no I. So I can have my -7, sum I is equal to 1 to, taking 4 from here and 4 from here, so you get me that, of 1. And so I know this, so I'm adding 7 numbers, so this top number is going to tell me how many, by making the bottom number 1, the top number tells me how many numbers I'm adding, and so I'm adding 7 numbers, and so this number should work out to me -49. And you can see back here in my working out, that's what it worked out to be, -49. Sweet, we're on the right path. So, if we deal with this other term, summation I is equal to 5 to 11 of 4i. Same as I did earlier, I took the, just going to come down a little bit, I took the 4 out as a common factor, so I can do the same, and I've just done it above here, so let's take that 4 out, and I've got sum I is equal to 5 to 11 of I. Now, one of the reasons why I want to do this is that if I get it as just an I, I've actually got a formula for it. I'm going to talk about that formula in just a second, but I've got a formula for that. So that's going to help me. But my formula is going to start at 1. So what I'm going to do is I'm going to say this is equal to 4. I'm going to put myself a whole big bracket around it. So if I go I is equal to 1 to 11 of I, what I've done, that's that bit up here where I've added those first 4 numbers in. So then I've got to take off sum I is equal to 1 to 4 of I. Now, so you notice how my previous sum started at 5. This bit that I'm adding finishes at 4, because if I made it finish at 5, I would have taken off that first 5 from the sum. First 5 from here. That's where it is. All right. Now, digression. Perhaps we'll just go sum I is equal to 1 to n of I is equal to n plus 1 on 2. This is actually something that they'll expect you to know for the exam. Okay, you will be expected to know that particular formula. So you should not take my word for it. It is your responsibility to check the exam conditions and rules. But I believe you are allowed to take in a cheat sheet. A couple of years ago I did a mock-up of a cheat sheet for AQMF, which you can still get access through our website. I humbly recommend you check every word on that page, because there's probably, even though I've had a couple of cracks at it, there's probably still typos in there. Okay? So if we go through it, I believe you are allowed to use that if you want. I don't recommend it. I recommend you make your own. But that's an example of stuff you could do. All right? Have the information in there. And again, don't use it without checking. Anyway, this bit. So it's going to be 4 by, so this one here, my n is 11. So I've got 11 times 12 divided by 2 minus, my n is now 4. 4 times 5 divided by 2. And so this is going to get me 11 times 12 is 132. Yeah, that sounds about right. So 4 by 132 on 2 minus 20 on 2. Whoops. So I'm going to get 4. And this is going to be 66 minus 10, which is 4 by 56, which I think I decided was 224. Yay, I believe that. Okay, and so I ended up, by breaking it down, I ended up with the same two numbers as I ended up in the first time I did it. So we hopefully have got the right answer. So, I'm going to leave that there for a couple of seconds. But what we're seeing there is that by doing this process of breaking up my summation, I can actually get all the bits that I'm looking for. All right? So, you may be asked to do, so just to remind you, this will appear online, so you don't have to worry if you've missed something. So let's go page 2. Okay, so what are my rules? So one of the things people have trouble with is when we write abstract rules in mathematics, it can be just a little bit confusing as what we really mean. All right. So we might write the rules and we might try and talk you through them. Having shown what's happening with these rules, if we write the rules and talk through what we're talking about, should be happy. So if I have some k a I is equal to, I'm just going to do 1 to n. All right. With this one, the limits of summation don't make any difference at all. All right. They're just numbers that I've included just to make the sum the same. Because this is k times this value, it's k times, if I write out what that would mean, it would be like k times a1 plus k times a2 plus, and we're going to finish with k times an. What that means is I can take that k out as a common factor. But I'd write that sum as I is equal to 1 to n of ai. Okay? So that is, if I have a constant multiple of that thing, of the thing inside, I can take it outside the summation, like I showed you just before. The next thing that can happen, so if I have sum ai plus bi, I is equal to 1 to n. So before you saw me break up into the bits where the 4 I bits and the minus 7 bits, this is the rule that sort of says, okay, I can break that into the sum of the AIs plus the sum of the BIs. And so we just add in the... So this is saying that if I have two bits, if I have a sum inside my thing, I can break it up. All right? So I think as far as you're concerned, so I'm just going to include sum 1 I is equal to 1 to n. This is a situation where those limits of integration are important because they're telling me how many numbers I'm adding. And so this is going to be 1 times n, or just n. We'll include the other one, I is equal to 1 to n of I. So again, this is that 1 plus 2 plus 3 all the way up to n. And so that formula for that one was n plus 1 on 2. And I don't think you actually need to know for the exam. But just because we can, this is going to be n plus 1, and then 2n plus 1, all on 6. So this is just the standard summation formulas that you're going to use. So there's understanding what the notation means, and there's understanding what these rules mean in terms of what you can do for your summation. The last thing to say is where you're going to see it. All right, so we've had an example of sort of how to do it in raw terms. There's where you're going to see it. The other thing to say is if it's a small number of numbers, if the number of numbers is sort of 10, 12, less than 10 or about 10 to 12, write them out, add them up. Seriously, my favourite phrase. Write them out, add them up. Because there's nothing wrong with just writing out. If you don't need to do a clever little trick with showing my summation rules. We can just saying these numbers, so let's just write them out, add them up, give me an answer. So, but where you're likely to see this in the exam, where it won't be just a case of write them out and add them up, it's going to be in doing an upper or lower sum. Okay? And so we're going to digress slightly into trying to do an example of upper and lower sums. Okay?
If that's like inverted, does that automatically become 3n plus 1?
No. It actually works out something like what is it? It's something like n by n plus 1 all squared on. I'm going to guess 24, but I'm not sure. So I know it's like n plus 1 squared, all squared sort of thing, in the numerator. I'm not sure about the denominator. If you really want, one day I'll show you how to go through and find it. So a dude Bernoulli actually spent a bit of time trying to work out the general form. And the answer is he created like a whole sequence of numbers to describe the general form, and it's kind of a bit bizarre. I digress. So we're good with that. Let's move on. So just going to put a line under that. So your upper and lower sums. So when I'm doing an upper and lower sum, I'm going to express this as is in summation notation. So typically we're doing an integral. So I'm doing an integral from, what I'm going to do is I'm going to go 1 to 4. I'm going to keep this function nice and simple. So I'm going to do something like 3x plus 2 dx. All right. So I'm trying to focus on, I'm actually trying to make this so that it's a bit interesting. Do I need to? Is that any better? Some of you look like you were having trouble reading that. So first thing we do when we do an upper and lower sum type of thing is we go, my A is the lower number here. So my A is 1, my B is equal to 4, and my interval width, which I refer to as delta x, is B minus A on n. So 4 minus 1 on n, which is 3 on n. And xi, which is always just a plus I times delta x, is going to be 1 plus 3i on n. So I'm going to add in my ith interval, xi minus 1, xi. I actually like putting that down so that it reminds me where my interval begins and ends, because that's actually a really useful thing to know when I'm trying to do this. and you'll notice that it begins at xi minus 1. All right. So my x naught is actually equal to a. So my first interval is x naught to x1. All right, or a to x1. Now, observation about the function. Function 3x plus 2 is, so my function is increasing. Right. Really important. So when I've got something which is either increasing or decreasing, it makes the sum, it makes the upper and lower sum thing easier to work out. So because I've definitely got an area. So it says that my maximums, so capital MI is equal to f of xi. So f of the right-hand endpoint of my ith interval. So the maximum for the ith interval is f of the x at the right-hand endpoint. And so because I've got f, so this is my f, and I've got xi, which is this, I can go, this is going to be 3 by 1 plus 3i on n plus 2. So I could actually expand this out and simplify it a little bit. So this is going to give me 3 plus 9i on n.
Can you scoot it up?
Oh, sorry. All right, there we go. Good. And so simplify a little bit more. 5 plus 9i on n. Okay? So I've actually taken the thing that I've got, simplified it a little bit. All right? Now my upper sum on n intervals. So this is a fancy notation saying upper sum, and n is the number of intervals I've broken it up into. So if your question asks for upper sum, and it has a little number there, that's the number of intervals you're actually supposed to use. All right? Someone showed me a question where it was like U5, and it took me ages to realize that they wanted 5 intervals. All right? So yes, this is what I mean, like you can overlook the easy thing to do in there. So upper sum is always, I actually like to put the delta x outside the sum. I is equal to 1 to n. So this is the sum for all intervals. All right, for every one of those little subintervals, we're going to add something. And that something is going to be the maximum value. All right, so xi times by every one of those values, but because it's times by all of those values, I'm putting it out the front of the summation, so it doesn't get confused in there. It makes my life easier not having it involved in there. The simpler the thing inside the sum is, the easier it is for me to work it out. So let's start putting in values. We've got sort of up here that delta x is equal to 3 on n. So let's put that, 3 on n. I is equal to 1 to n. And then we've got that maximum simplified. 5 plus 9i on n. So then I'm going to go back up and use my rules. I've got something plus something in here. So we're going to go 3 on n. It's important that we be careful with using brackets to say what's multiplied by what. When I'm splitting this up, it's important that I put brackets around the whole thing so that I don't get confused about what's happening. If I put my 5 here, plus my sum, I is equal to 1 to n, 9i on n. Going to try just a little bit more, 3 on n. So this first part is 5 by the 5 summation of just 5. So every time I increases, I just add 5. 5 plus 5 plus 5 plus 5 plus 5. So this is going to get me 5n. This bit here, every term is actually multiplied by 9 on n. So I can put that 9 on n out the front and do my summation. I is equal to 1 to n of just I. Okie dokie. So I'm just going to move that up a little bit. So my upper sum on n intervals so far is looking like 3 on n by 5n plus 9 on n. I said further up the page that this sum can be written as n times n plus 1 on 2. Now some algebra. So far we've just done a little bit of manipulation of our sums, a little bit of algebraic manipulation of our sums. We're going to ignore that detail. We're just going to start expanding stuff out. So if we look, I've got 3 on n times 5n plus 3 on n times 9 on n. And this bit here is going to get me n squared plus n on 2. Right? There's implicitly brackets around that bit, okay? Whenever we see a fraction, we've implicitly got brackets around it. To avoid making a mistake, we actually put those things there explicitly. So here, my n and my n cancel, and so I can be left with 15. Here I'm going to get something like 27 on, plus 27 on n squared. And then, so I'm going to do n squared on 2 plus 27 on n squared times n on 2. Whoops. That is not what I meant to write there. That number should be a 2. And so here again, my n squareds are going to cancel. So I'm going to be left with 15 plus 27 on 2. So my n squareds cancel. This term here, I've only got one n to cancel, and so I'm going to get plus 27 on 2n. Okay? Yep. Oh, put it up. Yes. Aha, sweet. Okay, so what we've done is we've used our summation rules to simplify this down. And so 27 on 2 is like 13 and a half. So 13 plus 15 is like 28. Yep, I believe 28 and a half plus 13 and a half, 1 on n. Now, so what we're seeing here with my sum is I've got a term which is a fixed number and my other bit which is dependent on n. Alright? Now, if you're asked to work out what the area is, what I'd do is I'd say, if I make n goes to infinity, you've talked about limits and everything, haven't you? Should have talked about limits in Introduction to Financial Maths. So, if I make my n go to infinity, this term here is going to go to 0 because it's got that 1 on n term. So as n gets large, 1 on n goes to 0. That bit disappears. And so my area is going to be equal to 28 and a half. I'm not going to worry about. So because the point about this was to talk about the upper and lower sum part, to talk about the summation part, that's exactly what's happening with the summation and how we're going to use it in a problem. All right, and that's how they're going to, more than likely, that's how they were going to ask you to show your understanding of these things, by making you do a problem where there's lots of where you actually have to do the calculation. Are we good with that? Do we want me to do more on that, or I'm aware that we've already got stuff on upper and lower sums, specifically about upper and lower sums on our website, not specifically about summation, but that's the sort of thing where we're going to see it happening. So our rules are sort of, we've got rules where we can break up the sum or take a constant out the front. We can add or subtract bits into the middle. Does that sort of help you guys with what you wanted to know? All right. Now what I could do then, like I say, I'm not inclined to do a lot more on that unless you actually want me to. But we're good. Anything else people want to talk about? Implicit differentiation. Okay, so you guys are going to go on and do economics. Let's see, what I might do. We might dither for a bit and split this. Okay, so what we're going to do is we're going to